Good morning for this last day of this wonderful workshop. I really have had a really amazing time here, and unfortunately, Dave is not here to. Oh, there you are. Thank you, Dave, for.
Thank you for coming.
Okay, so I was telling you about quantum fields. This is just a recap. I mean, the reason I have it every time is because that's, like, if there's one thing I want you to remember, like, I want you to remember the rough shape of this. But I was telling you about quantum fields, and I'm afraid that I wasn't as clear as I wish I had been. So let me just repeat a couple of things that I said yesterday. So first of all, quantum fields it can mean many things. It comes in a hierarchy of more and more complicated variants of the notion. And the one that I defined at the beginning, namely the primary fields, those that correspond to vectors in the vacuum sector, which are eigenvectors for the energy operator L0, and which are annihilated by all the energy lowering operators Ln. For n bigger than 0, Ln is an energy lowering operator. Those things, that's like the easiest type of quantum fields that correspond to those. These are quantum fields which are, so quantum field can be either primary or, and then the standard terminology, the opposite of primary is descendant. And then there's another thing that the quantum field can be or not be. I've talked about things that correspond to vectors in the vacuum sector, but there's also things that correspond to vectors in other sectors, and these are called charged fields. And this is really 4 different categories. A quantum field can be primary and in the vacuum, can be primary and charged, can be descended in the vacuum, and can be descended and charged. Like 4 different things, this being the most general one, all of the other ones being special cases of. Something which is primary and in the vacuum will satisfy phi of z. So the way you often write it is just phi of z, but this secretly depends on a choice of vector at the tangent space at z. And so let me be explicit. Let me put the vector there. And let me change my mind and put a scalar times my vector. So now I have a times b. And the equation says that this comes out as a to the delta phi of z. And this is for some delta, which is an integer. Primary fields which are charged will satisfy the very same equation, except delta is no longer. So this equation here means primary, and this condition here holds only in the vacuum. For charged sectors, it doesn't need to hold. And then you'll have to think about exactly what this means. That's a scalar to some power which is not integer, but we'll come back to that. And descendant fields are things that, in order to, well, just like here, when you're sort of sloppy writing things, you just write phi of z. Secretly depends on something else, and that something else in here is going to no longer be just a vector. It's going to be, well, what's a vector? A vector is a trivialization of the first order infinitesimal neighborhood of your curve. It's like you take the curve and you take just the information of derivatives, but not the information of second derivatives, and you trivialize that. And here you'll need to trivialize it up to a given order. So, so now this is going to be a thing that you write as phi of z, comma, j, where j is a jet, an n jet, at the point z on the Riemann surface. Okay, so let me spend a bit more time on this. So how does it work? You start with, so unlike these can be nicely axiomatized. I wrote a definition, which is like, then there's a theorem. Like, these, I guess you could try to do something like that, but it's better to think of it as being a constructive thing. I start from a vector in the vacuum sector, and I'm going to assume that this is an eigenvector for the operator L0. I could be a little bit more relaxed and say I want it to be a finite sum of eigenvectors. Such things, vectors which are finite sums of eigenvectors for L0, these are called finite energy vectors. And the vector space of finite energy vectors is the vertex algebra that corresponds to this story. So I take a finite energy vector, Xi, and then there is going to be a number such that this is 0 for every, I mean, right? These are, so there exists a number d such that this is 0 for all things that are bigger than d, right? I mean, it has finite energy. And if I take things that lower the energy by more than that energy, then it's going to be 0. There's just nothing there. So that's what this condition buys you. So there's going to be a relevant, or like this n here and that d there are just the same number. So I'm going to call that the order d jet. So what is a jet? Just to be, we'll be working with this, so let me be specific as to what I mean by that. So a jet maybe I put it down here. A jet is a map. The way I like to think of it is as spec of C of z modulo z to the d plus 1 to sigma. So recall that I defined these things as ringed spaces. This is also a ringed space. The underlying topological space is a single point, and the ring is the ring that I have there. What's a map of ring spaces? Well, the map of rings the other way, from holomorphic functions on sigma to this. And really what this is, it's picking a point in sigma, and it's picking, you can think of this as being an equivalence class of maps from an open neighborhood of the origin in the complex plane into sigma, where two such maps are declared to be equivalent if they send 0 to the same point. That has to be this point z. And the first derivative, second derivative, up to the derivative agree, and that's all. So that's either you think of it as a single map or as an equivalence class of maps from something which is a genuine, like, little disk. So these are equivalent ways of thinking about the jet. It's going to be important to understand what happens when I replace a jet by some other jet. Like here, we have replacing a vector by another vector, and the only thing you can do is multiply by a scalar. So there's going to be a group which is going to play the role of, here, C star. So let's call that group G sub D. G because it's a group, sub D because it depends on D. That's going to be changes of ordinate defined up to degree. OK, that's the informal way of thinking about it. Really what it is, it's the automorphism group of C of Z modulo Z. The automorphism group of this ringed space, equivalently the automorphism group of this ring. If you have two jets at the same point, their difference is an element of that. So the Lie algebra of this algebraic group is the Lie algebra of GD. So this is a group which is d-dimensional, and the Lie algebra is just a subalgebra of the Virasoro algebra. That's not quite right. So it's a quotient of a subalgebra. So here this notation means you include the operators L0, L1, and so on up to LD minus 1. Really what this is, it is Virasoro greater equal than 0. That's a subalgebra divided by Virasoro greater equal than D. So that's a sub-Lie algebra. That's a normal sub-Lie algebra of this. You take the quotient, and that's a finite dimensional Lie algebra. The Lie group corresponding to this is this algebra. So now that we have these things, we can write. So remember that one of these things, phi of z, is a modifier of this thing. You have a Riemann surface, sigma, which is going from S1 to S2. Without any field insertions, you have a linear map like that. With some field insertions, you again have a linear map like that. It's just a different linear map. So you just put the thing, and it modifies this. So the formula is, so let me have my Riemann surface. I call it sigma. And then I have some points, Z1, Zn, not the same n. And of course, I don't need to put the same field at each one of these points. I can put a different field. So I'm just going to put an extra index, psi I, where I goes from 1 up to n. Each psi I has finite energy, and for each psi I, there's going to be a di such that this equation holds. And at each point, Z1 up to Zn, I'm going to put a jet of order D, and the D is going to be the relevant D for the point. Like I can put a primary field here and one which is not primary there. If I put the primary here, I only need a tangent vector here, and over there I'll need a bit more. So then how did the story go? There were some maps. Fi from the standard disk to sigma, mapping 0 to the point Zi, and having non-intersecting images. And then we defined the surface where we punch holes in it, sigma 0 to be sigma minus the union of the images of Fi. And being a tiny, tiny bit sloppy, I need to take the image of the open disks. Otherwise, it's not compact. So I put a little circle over it to just say open disk. Put it there. Great, so we have these Fi's. And then the formula is Z sub sigma modified by phi 1. Okay, phi 1 is the quantum field corresponding to psi 1. Phi 2 is the quantum field corresponding to psi 2, and so on. So phi 1 at Z1 using the little jet J1 dot 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 up to phi n Zn Jn is going to be equal by definition to, well, I need to define it in terms of the stuff I have, and the stuff I have only talks about like composites without field insertions. So I need to define it in terms of Z sub sigma 0. If I had arranged things so that these maps Fi are representatives of the jets Ji, then I wouldn't need to do anything very complicated. I could just write down, put in the vector C1 at the first entry, and so on. But this is something that cannot be guaranteed, and therefore okay, so what is this? This thing is a map from something to something else. Let's also take a vector and feed it to this map. So I take a vector eta, and that's going to be the last one. So eta is in here. Okay, what are the G's? The G is the difference, the ratio in this group between the F's, between what I want, which is the J's, and what I have, which is the F's. So put it up here. Gi equals Fi inverse circle Ji. And that's an element of G Di. The Gi's that appear in this formula are given like that. And then a thing which I didn't do yesterday was to show that this is a well-defined thing. I mean, yesterday I did it only for the case of primary fields, and I gave you that formula, or the equivalent of the formula, and I just said, OK, this is it. But let's actually check that this is independent of the choice of little fi's that we have. So we have these maps. So we have the standard disk here. I'll draw it. And then we have these maps. We have here F1 has image there up to Fn, an image there. And then I change these maps while preserving this property that 0 goes to Zi. I want to know that this thing isn't changed. If I change it arbitrarily, it could be that I'm just moving it a bit to the left or to the right. But it's enough to show that by shrinking it or by enlarging it, it's the same. Because by combination of shrinking and enlarging, I can go from anything to anything else. So now I'm going to assume that I have a different set of these guys, and that the images, these red circles, become smaller. I'm going to show that this formula is unchanged. So now I have a different set of these. Here, I'm going to overload this picture. Sorry for that. I have now the same sort of stuff, except now these are F1 tilde, and here this is Fn tilde. So it's a new choice of things, and you can write the very same formula. Everything acquires a tilde. So now we're going to have G tilde equals F tilde inverse composed with J. And then we put the G tildes in there. And there's also sigma 0 tilde, which is sigma minus the image of these guys. And so we just look at the formula. So the new definition of Z tilde of sigma by 1 of Z1 J1 dot of eta equals, by definition, namely by just copying this, sigma sub Z sub sigma 0 tilde of G1 tilde C1 tensor, and then at the end we have eta. So here's something useful. Between these two guys, there's a bit of space, and that is an annulus. So let's call this annulus A1. An annulus with parameterized boundary, because we have this superrepresentation, F1 and F1 tilde. Specifically, this annulus comes from a univalent map of the disk. If I look at the red disk, I can go back via F1 and then go via F1 tilde. It's a map from the disk to itself. So this annulus is something that's going to be useful. So I can rewrite sigma 0 tilde as sigma 0 composed with this annuli. So that's Z sigma 0, and then Z of A1 applied to G1 tilde C1 and okay, so then I can introduce psi I, which is Fi inverse composed with Fi tilde, and that's an element of the semigroup of univalent maps. And acting by this analysis is really the same thing as acting by this thing here. So that's the same thing as putting psi 1. That's really the same thing. And then psi 1 composed with G1 tilde. If you look at the definition of the psi and the definition of the G and put them next to each other, what does that do? Well, it exactly will remove. So the G tilde is this formula with a tilde on this F. And then I compose it with that formula. And guess what? The two F's with tildes cancel out. And it replaces the one that you didn't want by the one that you want. So then this is the same thing as G1. And then we're back to exactly this formula. So that's just a check that this formula is well defined. I want to make this a little bit more concrete by working out in a particular example what is the analog of this transformation law. Here I just said you can do a bunch of things, but if you're faced concretely with something, how do you transform from one jet to another jet is not completely straightforward. And so I want to do there's a quantum field which is very important, appears not just in conformal field theory, but sort of in a very big level of generality. That's called the stress energy tensor. And it's denoted T of Z. And it's a field which is not primary. And it's a field which corresponds to, so this is a standard letter. You're not allowed to change this letter. But the vector that it corresponds to is, so you take something that has the vacuum. So, take your CFT, and the vacuum sector always has an action of this semigroup of analyzed. It has an action of the Virasoro algebra. So, and it also always has a vacuum vector. And so I can take my vacuum vector and hit it with my preferred Virasoro algebra element, and I will get something. And the first thing that you always have, and which is always non-zero, is a thing which is standardly denoted by little omega, which is L minus 2 of the vacuum vector. This is called the Virasoro element. And that's the one that we're going to take for what was denoted here, Xi. So we take this specific thing for Xi, and then we run this machine, see what we get, and we get a field which is called the stress energy tensor. OK, so let's first check that this is indeed, as I told you, not a primary field. So I'm going to first compute L1 of omega. So that's L1, L minus 2 big omega. And then you use the Virasoro commutation relations, and then that's like 3 L minus 1 omega. And I claim that's 0. Why is that 0? Because L1, L0, L minus 1 together are a generator of a three-dimensional group of Möbius transformations. Namely, these are things that naturally act on H0 because H0 is built from the disk. And also, the vacuum vector is built completely canonically just from the disk, and therefore it's invariant under that. So this is 0 because this Lie algebra, the Lie algebra of the Möbius transformations, fixes omega. Okay, so this is a thing that's in energy 2. So if I lower the energy by 1, it happens to be 0. So that's, I guess, good. The other thing that could happen is that you get something non-zero when you lower the energy by 2. So that's L2, L minus 2 omega. And then again, you use the Virasoro commutation relations, and you get 4 L0 omega. And that's 0 for the same reasons. Plus, and then you have the Virasoro cocycle, C over 12. And then you compute it, and you get 6 times omega. And all that is equal to C over 2. So little c is the central charge. And guess what? That's not 0 in most cases. It's not primary. It doesn't satisfy this equals 0 for all n bigger than 1. It satisfies it for all n bigger than equal than 3. So we'll need to use jets of order 3 to describe this thing. So it's, I guess, useful to write down. So this group which acts, here I wrote this group action at the level of the Lie algebra. The relevant Lie algebra is generated by L0, L1, and L2. And this vector generates a two-dimensional representation of the group, stand by this and that. So little omega and big omega. So let me just write down in a chart. So the action of Ln on big omega and for Ln on small omega when n equals 0, n equals 1, and n equals 2. These are given by the vacuum is just fixed by everything. So at the Lie algebra level, you get this, and this, we just computed it. This is energy, has energy 2, so that's an eigenspace with eigenvalue 2. That's 0, we computed it here, and that's C over 2 omega. So that's a very explicitly given Lie algebra representation of this small Lie algebra. Now we're in the case d equals 3. So three-dimensional Lie algebra on a vector space spanned by little omega and big omega. We don't want an action of the Lie algebra. We want an action of the Lie group. And as you all know, it's possible for abstract reasons to always integrate that. And it's messy to do it with explicit formulas. There's a thing called the Campbell-Baker-Hausdorff formula that that will do it for you. And I will just give you the answer, because the answer is kind of thing that you can check, but it's kind of messy. So at the Lie group level, this becomes, for G in G3, this becomes, this one is easy. Big omega is just fixed. That's little omega. That is, well, there's going to be this contribution, which is easy. It says that, roughly speaking, it's like this formula with delta equals 2 plus a correction term. A correction term coming from this. And what is the correction term? Here it is. Ready? It's like C over 12. That's the thing that you expect because it just appears from here. And the next one is third derivative divided by first derivative minus 3/2. Second derivative divided by first derivative, all that squared. Huh. That's an expression that appears often enough in conformal field theory and also in other areas of mathematics that it has a name that's called the Schwarzian derivative. And so I can then use this to write for you what is known as the anomalous transformation laws of the stress energy tensor. And here I'm just going to fit it in here. So it says that T of, if I have a point W and a 3-jet, which is obtained by a given one by composing by a function, then that's the same thing as f prime at 0 squared T of, by putting the thing at point W, comma J. So that's a formula that you have by copying this, and then plus a certain C over 12 times, there's a name for this thing. This is denoted GZ curly brackets. That's the definition of this notation. And then C times FZ. This is all at 0, so this is at Z equals 0. And this is times the vacuum. So this is really in this box, in this lower left box. You just didn't have enough space in this box to put it there, so it landed there. But really, it's about a certain field in the vacuum, the field corresponding to that vector here. So that's an example of how these things might transform. And it's one which is particularly important because it always exists. It exists in any conformal field theory. I didn't need to assume anything special about the conformal field theory for this to be able to be written down. Okay, so
sorry, is it not possible for omega to be 0?
For little omega to be 0? It is possible for this to be 0, but only when the conformal field theory is very degenerate. Namely, if this has only one object, and if this functor sends this object to the one-dimensional vector space, and if everything is trivial, then that vector is 0. Otherwise, it's not 0. Okay, so there's one structure which is really important in conformal field theory that I didn't get very much time to talk about, and that's a bit of a shame, and that's the fusion product. The fact that when S is a circle, this category is not just an only category, but it's a, well, first of all, it's a monoidal category, and then it happens to be braided. It's not symmetric, just braided. And then it also has a twist, and then it's also, eventually, it's a modular tensor category. So well, let me tell you a little bit about how that goes. So the monoidal structure, the product from that category to itself, across itself, back to itself, is what you obtain when you take this thing as your sigma and plug it here. So this will produce a functor which is called fusion. And this immediately raises the question of which sigma did I take? Because I drew it like that, and there are some choices about like how big the circles are. Do I take them to be circles or not circles? Are they on the x-axis or on the y-axis? So the easiest way of dealing with that is to say they are actual circles. They're actually aligned on the x-axis. But still, there's this question of size. You can't, I mean, I could commit to center them around -1/3 and +1/3 with radius exactly, I don't know, something. But it's better to say that whatever I choose, any other choice that I make is going to differ by something like that, or by a sequence of things like that. You make them a bit bigger, a bit smaller, and then like move them along the x-axis. These are analyzed that come from the semi-group of univalent maps. So there's no central extension problems. The central extension goes away. And so associated to this, there is an equivalence between the functor that you assign to this and the functor that you assign to something with slightly smaller. So this tells me that the exact size of holes doesn't matter because of this piece of data here. Now, I told you it doesn't really matter where you put them on the x-axis and how big they are. There's nothing that tells me that they have to stay on the x-axis, because they can go up and down. It also doesn't matter. And by taking these two circles and making them a bit smaller, a bit bigger, 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 you can actually slowly translate them. Like if I have a circle, and I made it a bit smaller. OK, now it's a bit smaller. Now I'm making it a bit bigger. That's a bit bigger. Now I'm making it a bit smaller. Now a bit bigger. A bit smaller, a bit bigger, a bit smaller, a bit bigger. You can sort of go around and travel with these things. And so what you get is that for any homotopy in the space of such pictures, you get a composite of these natural transformations and their inverses that will allow you to go from one such functor to any other functor. And if you go from this to that by slowly going around, you see that this thing is actually braided. You get the natural transformation from this thing to the same thing where the two inputs are reversed. So this is braided. I should have been specific that in order for this to be really S1 as opposed to some abstract circle, these need to be parametrized. The boundary and these two things need to be parametrized. And I'm going to indicate it on the picture by keeping track of where the element 1 goes under these parameterizations. So another thing that you can do, in addition to this type of motion, is to let the little blue dot that signifies the image of 1 rotate. And that's another thing you can do, just like make it bigger, a bit further. And as you do that, the dot sort of moves around. And so the ability to do that, the fact that I can take this picture with these two dots and that one sort of rotates around, means that the category is equipped with what is known as a twist. It's and a category which is braided and equipped with a twist is called balanced. You can also get that structure directly in the following way. That's a sort of like, let's try to remember where A tilde lived. I mean, I sort of had it on the board all these previous times, and right now I didn't write it. It lives in a central extension of the semi-group of annuli that has as its center C star cross Z, and then here has the central extension, and then goes down to N. For the purpose of this particular discussion, I picked, say, all my circles to be round, and so this part of the central extension does not play any role. So that goes away, but the Z is still there. And so I can take A tilde to be the trivial annulus plus the non-trivial element in the center. It's like I take it to be the central element that generates this Z. And that induces a particular natural transformation from the identity to the identity. And that is known as the twist. And that's the thing that you get as an additional piece of structure that makes its fusion category not only, I forgot an R, braided, but also balanced.
Non-degeneracy of braiding is another thing. Right?
Sorry?
The non-degeneracy of the braiding is another thing.
You cannot see it easily. Just, I mean, this is just very soft. This will not get you anything such as the non-degeneracy of the braiding just by looking at this level. You need to do
so this is operator analytic spaces. So are we looking at something like operator analytic minicourse with complex coordinates? So they look pretty like E2 opera, zero disk opera.
Yes, this is, yeah, so what you have is for every, so there's a particular topological space, which is the space of all embeddings of n disks into one disk. And for every point in that space, there's a functor. And for every homotopy class of path in that space between 2 points, there is a natural transformation. And so this is the structure. Yeah, that's equivalent to the structure of a balanced tensor category. So, okay, so there's this space that I told you about, like a disk with a bunch of little disks in there. You can also put a bunch of little disks on some other surface, which is not a big disk. That's a thing that you can do. So I'm going to fix the complex homomorphism sigma, and I'm going to look at a space which I call disk n of sigma, and that's a topological space, which is a set of n tuples of holomorphic maps Fi from the standard disk to sigma and I'm going to require that they have disjoint images. So exactly what I did here for sigma equals the disk, I can do it for some general sigma. And then for every point P in that space, we get a functor which has well, let me abbreviate this. This I just called C. The category associated to the standard circle, I call it C. And the category associated to, well, in this particular, to this manifold, I call it explicitly what it is. So for every point, we get a functor like that depends on the point. And for every path, from P1 to P2 in that space, we get, well, we get two functors. F, let's call them just like F1 and F2. And if I give a name to my path, if I call it gamma, then so gamma is a thing that you can model by something like that. And then you can get a big composite of these trivializations, go up and down and up and down and up and down, and then you get a natural transformation. T sub gamma. And I use the letter T because I had used the letter T for that, and this T in green is just a composite of those. A thing that I want to point out is that these operations of going smaller and bigger and smaller and bigger and smaller and bigger, at each given time, we have a parametrized disk and another parametrized disk, and the space in between. So if you, let's see if I can find, or maybe it's, I'll just have to draw it here. So I have one of these disks, which I'm emphasizing here in red. And then I make it smaller. It's here. And the stuff in between is not an arbitrary annulus. It lives in this sub-semi group of univalent maps. This is parametrized, that's parametrized. And therefore, it's a thing where there's no it's on the nose. It's not up to an anomaly. And so what we see is, in particular, if I restrict to the special case. So now I'm going to make things simpler. I'm going to assume that this is closed. So I have nothing there. So that's going to get rid of that. I guess replace it by the category vec and get rid of that. And now I'm going to also assume, to make things even simpler, that I have chosen objects lambda 1 up to lambda n in C. And I'm putting these objects here. So lambda 1 and lambda n in C. So now I have a functor going from C times C times C times C to vec, and I have chosen objects. Well, it means I have a chosen vector space. This vector space ends up being finite dimensional. That's a thing that you can show for us from the axioms. And saying that there's these natural transformations is saying that there's an action of the surface braid group on this vector space, which is really the pi1, the fundamental group of this space here. And so you might have heard the fact that, like, from conformal theory, you get actions of mapping class groups and actions of surface braid groups. Here, I want to be a bit more specific and say the braid groups act honestly. The braid groups act without any projective, without any anomaly. The mapping class group is also a thing that acts on the same vector space, namely the image of lambda 1, lambda n under this. This is just, this has become back. And how does the mapping class group act? Well, if you imagine your surface is like that, and I want to replace it by another surface, the thing that we can do is, for example, chop it in the middle, like a bunch of, and then somewhere I see an analysis. This is an analysis. And then I'm like, OK, well, I'm going to remove that analysis. I'm going to directly glue this to that by using one of these trivializations that you have there that tells you acting with an analysis is the same thing as doing nothing. And by doing these things of adding analysis, removing analysis, you can slowly deform your surface. Like, you keep the genus, but you can go from any surface to another surface. So that allows you to have an action of the mapping class group. But here, these analysis are just general analysis. So you have the anomaly. So the mapping class group acts in a projective way on these finite dimensional vector spaces, but the surface ribbon braid group acts in an honest way. And yeah, so that's brings me to the end of the hour, and that's also the punchline that I wanted to reach.
How difficult is it to see that this category has duals?
There is a thing called weak rigidity, which is not too difficult to see. So in the string diagram calculus for monadal categories, if I have objects A1, A2, A3, A4, B1, B2, B3, then you can look at the space of maps from A1 tensor up to A4 into B1 up to B3. That's a certain finite dimensional vector space. And you can ask that there be a canonical, well, that for every object there's another object called the dual, and that there's a canonical bijection between B3 has gone down, and then the requirement that there's a collection of canonical bijections between all these things is the requirement of weak duality. That's not too difficult to see. Now, a thing that you might be guessing is that if I call this alpha and I call this alpha tilde, you might be guessing that alpha tilde is equal to the following thing. I take alpha, which goes like that. I take this, here I have the identity. I can use identity tilde, and I can do that. The requirement that this equals that, that's the difference between just being weakly rigid. Weakly rigid is the existence of these bijections, and the requirement that these two be the same, that's being genuinely a category with duals. So this is rigidity. So it's easy to see weak rigidity. It's hard to see rigidity. The only proof that I know is formulated in the language of vertex operator algebras, was written up by Yiji Huang, and is a rather elaborate argument that I could tell you about this afternoon if you want.
So in particular, that you have to use this complex analytic structure beyond just a modular functor in some non-trivial way.
Yes. So if you call this left column the modular functor, then it is not known. It's a major open question whether this structure alone implies rigidity. The proof of Huang of rigidity uses this in a very essential way to get that result. Yeah.
This is maybe a quick comment which fits into that story is in the classification of 3-2-1 TQFT, you need to have non-invertible 3 manifolds to get rigidity. And this other property you can get from invertible 3 manifolds fits into that. Sort of interesting that the non-invertible 3 manifolds cannot do the same job as the conformal structures in this setting.
Yeah. I think it would be interesting to see if there's parallels between the two proofs.